Having log-likelihood ratios, we can now see how we can apply log-likelihood ratios to the decoding problem of LDPC codes. So first we look at how we can use log-likelihood ratios to decode a repetition code. So we will see later what a repetition code, or what is the relation of a repetition code and an LDPC code. So first we assume that we have a repetition code of length n, where we transmit a bit x equals 0 and we receive a vector y, y1 up to y sub n. And we assume the bit x equals 0 is uniform. Uniform prior, so x equals 0, probability x equals 0 is probability x equals 1 is 1/2. So in order to make a decision, we calculate the a posteriori log-likelihood ratio, because then we can get the a posteriori probability, which we can use to make a decision. So we calculate L of x given the received vector y, and because a posteriori is equal to a transition log-likelihood ratio, if we have uniform prior x, this is equal to L of y given x. So this is then equal to L of P of y given x equals 0 divided by P of y given x equals 1. And this is something we can express then, because we assume that it's memoryless. So P of y given x is equal to the product of P of yi given x equals 0. Each position, it's a repetition code, will transmit the same x. Transmit x equals 0, we receive y1. Transmit x equals 0, we receive y2. X equals 0, y3, and so on. So this is equal to the product of P of yi given x equals 0 divided by the product of P of yi given x equals 1. And this, the log of a product, is the sum of the logarithms. So this is the sum of the log of P of yi given x equals 0. And this is the channel transition log-likelihood ratio. So we can get the following result. So the logarithm, or the log-likelihood ratio of x given y, is equal to the sum of the log of yi given x. So it's essentially the sum of the channel transition log-likelihood ratios. So how can we now realize a map decoder? So a map decoder for the repetition code takes the log-likelihood ratios for the channel output and adds them up. And then we do a decision x hat is equal to 0 if this a posteriori log-likelihood ratio is larger or equal than 0 and x hat equals 1 otherwise. Essentially, we calculate the sign of the sum of the channel transition log-likelihood ratios. This is the map decoder, and this is the map decoder for any channel. This is the map decoder for the binary input AWGN channel. This is the map decoder for the binary symmetric channel, and for any other channel where we can calculate log-likelihood ratios. You recall the map decoder for the binary input AWGN channel for the repetition code we derived by hand without log-likelihood ratio. Essentially, this is the sum of the received values, and then we look at which is largest. This is the same here because we multiply the received values by a constant. That's what happens inside L. This constant doesn't change the sign. So the sign just depends on the received values and not on some constant. So that's the repetition code. So what is the context to LDPC codes now? If we look closely at a variable node of degree dv is essentially a repetition code. So one bit of this repetition code is transmitted over the channel, and the other bits of the repetition codes, they are transmitted over the graph. So we get information about this bit from multiple sources that come in the graph. And we get information from the channel. One bit of information from the channel. And then also in the graph, we get messages telling us how reliable this bit is, or what is the probability of this bit being equal to 0 or 1. So now we do the same as in soldier counting. So we start collecting messages that we get. And once we have collected dv-1 messages, we send out a new messages. We send out a new message. So we have a message from here, that's from the channel. We have a message from this check node, from this check node, from this check node. Now we have collected dv-1 messages. This one is present a priori. And now we calculate an outgoing message that we send to the next check node. So we use some views of notation. So we denote this message by L of chi that we get from the check nodes. So these are the messages that we get. And then we can calculate an outgoing message, L of C. And essentially we decode a repetition code. And we'd like to get the information about this repetition code. So we have the information from the channel plus the information from all the other messages. L of C4 is equal to L of yi given xi plus the sum over all the other messages, so the sum of L of chi. So that's how we can calculate log likelihood ratios for repetition codes, and also in the context of an LDPC code, where the variable nodes, they are essentially repetition codes of the log likelihood ratio, or of this bit that is repeated in the context of the graph. So it's sent to other check nodes, and we get information from the check nodes. So we repeat it and send this bit to the check nodes, and then we get information back from the check nodes. All right, so for the other edges, we get messages that we can plug in a similar way. So for the first edge, L of Ci is L of yi given xi plus L of chi2 plus L of chi3 plus L of chi4, and so on. So the important part is that we exclude the edge under consideration from the computation. This is what we call an extrinsic message. It's the same as in soldier counting. So we don't want to send the guy what he already knows. We want to send the guy who's sitting in front of us what we get from all the other guys. So we wait until we get all the information from the other guys, and then we can tell the guy in front of us what we know. Here it's the same. So we don't want to tell the guy what he knows already, but we want to tell the guy, which is a check node in this case, what he doesn't know. So we exclude the message or the edge under consideration, and you see that the one for which we compute a message is always missing here. Now, if you want to make a decision on the bit xi, then we accumulate all the messages from the edges, and we calculate the a posteriori log likelihood ratio. So we calculate L of xi given y is even to the channel log likelihood, to channel transition LLR, plus all the 4 incoming messages from the check node. So that's how we can calculate the a posteriori log likelihood. So now we take a look at the check nodes. So the check nodes essentially is a single parity check code, because we have to fulfill a parity check equation. And before we move on to the particularity, we need to know how to calculate the probability of a certain digit is even in a check node. And that's why Gallagher's lemma comes into play. In Gallagher's lemma, we have a sequence of zeta digits. We have x1, x2, up to x zeta. And we would like to know what is the probability that this sequence has an even number of ones. And we know that the digit at position L is 1 with the probability PL. So each digit in this sequence can have a different probability of being equal to 1, and we call this PL. So now we calculate the probability that this sequence has an even number of ones, and this probability is given by this expression. This probability is given by 1 plus the product of 1 minus 2 times PL divided by 2. Maybe this sounds familiar to you. Recall the previous video, we calculate the expectation of a bipolar binary random variable, and we got exactly this expression. So how can we prove this fact? There is a very elegant proof by Gallagher. You already did something similar in the tutorial when you calculate the concatenation of binary symmetric channels. That was essentially similar. If you concatenate binary symmetric channels, probability that you have an even number of ones is the probability that you don't make an error. Because if you make an even number of errors, you go back to 0. And that's exactly the same expression. So try to bring this together with what you did in the tutorial. And here we can look at the way Gallagher proved this. So that's a very elegant way, because what Gallagher did is he looked at the function f1 of t, which is the product from L equals 1 to zeta of 1 minus PL plus PL times t. And t is just some variable. So for the time being, imagine t just being a variable, just a formal variable. So what we do is, we don't like products. So what we do is we expand this into a polynomial. So before expanding this into polynomial, we assume that this is a one factor and we have the other factor. So let's do it for zeta equals 2. Very difficult to write at zeta, not a c. Zeta equals 2. We have 1 minus p1 plus p1t times, and let me actually move this here where I have a little bit more space, times 1 minus p2 plus p2 times t, and we group it that first term is together. So this is equal to 1 minus p1 times 1 minus p2. We first multiply the constant terms. Then we have 1 minus p1 times p2 plus p1 times 1 minus p2 times t. And then we have plus p1, p2 times t squared. So that's how the expansion looks like. And in the general case, we can do the same expansion. So we have all the terms multiplied with 1 minus pi. And then we have the summation of all the factors that contain a single p. And all the other terms are 1 minus pi. So it's p1 times 1 minus p2, 1 minus p3, up to 1 minus p zeta, plus 1 minus p1 times p2 times 1 minus p3, 1 minus p4, and so on. So we have all these terms times t. Then we have all the terms with 2 pi, so pi, pj, and then all the other terms are 1 minus pk, and so on. So we can see that this term is the probability that we have 0 ones in our sequence. This term is the probability, so let me wait until this vanishes. So this term is the probability that we have a single 1 in our sequence. This term is the probability that we have 2 ones in our sequence. So essentially, the coefficient of ti is the probability of having I ones. So just by extracting the coefficients of this polynomial, which is also called a generator polynomial because it generates the probabilities, coefficient of ti is the probability of having exactly I ones in the sequence. Now we want to have the number of even, the probability that we have an even number of ones. So we need to get rid of the odd exponents somehow. So how do we do this? Well, we do this by looking at a similar polynomial, as a similar function, but we put a minus here. We put a minus over there, and then the odd powers of t become negative. So just because of this minus, the function is identical, but the odd powers of ti, they become negative. So now what happens if we add f0 plus f1? We essentially double the even powers because they are accounted for twice in this sum, but the odd terms, they will cancel out. So essentially f0 plus f1 of t is 2 times this term, which is the probability that we have 0 ones in our sequence, plus 2 times p1, p2, 1 minus p3, and so on. So this is the number of terms, or the probability that we have 2 ones in our sequence. So the number of terms is here in the sum. We essentially have, there we go. We essentially have, theta choose 2 terms in this sum. So times t squared and so on. So now, how do we get the probability that we have an even number of ones? So this is the probability to have 0 ones plus the probability that we have 2 ones plus the probability that we have 4 ones is then assigned to t to the power 4. So we need to add those coefficients. How can we do this? Well, we need to get rid of the t somehow. How can we get rid of the t? Well, we just evaluate this polynomial for t equals 1. So this polynomial, this is f0 of 1 plus f1 of 1 times 1/2. We have this factor of 2. The probability of having an even number of ones. Okay, so now how do we simplify this? Well, we just write out f0 of 1 and f1 of 1. So this is the product of 1 minus pl plus pl. We see that minus pl plus pl cancels. It's a product of 1. It's just 1. Plus the product from 1 minus pl is 1 minus 2 times pl. So we have the expression 1 plus the product of 1 minus 2 times pl divided by 2. All right. So next we can take a look at the case when we want to have an odd number of ones in the sequence. That's a simple corollary of this proof. So the probability that we have an odd number of digits in the same sequence is just 1 minus the expression. Either you can see it as a corollary of the previous lemma by calculating 1 minus this expression, or you can prove it along the same lines, but you calculate f1 of t minus f0 of t, because then the even terms will cancel and you will just be left with the odd terms. And then you can do the same simplification again. So here, I see there is an issue, this t that should not be there. And let me take a quick note to fix this in the errata. All right. So this is the case here. So what we have is the following. We can now take a look at a single parity check code. So we have a single parity check code of length n, which has n-1 information bits, parity bits, and we transmit the code words over a memoryless channel. Again, memoryless channel, output is y. So the bits in the code word xm, they have a constraint. The number of ones in xm must be even. That's the single parity check constraint. So now let's take a look at map decoding of the single parity check code. So x1 hat is the maximum of p of x1 is equal to b, given y, and given the fact that we have an even number of ones in x, because we have a single parity check code. So instead of putting the code constraint in the maximization, I can also put it in the condition of the probability. So we can rewrite this a little bit. So the probability that x equals 1 given y and having an even number of ones in the constraint is the probability that x2 to xn has an even number of ones given y. Because x1 is equal to 0, we want to have an even number of ones, x2 to xn should have an even number of ones. So that's simple because we can now just plug in our expression from beforehand. That's 1 plus the product from n equals 2 to n. So now we have a sequence of theta equals n minus 1 digits. So theta equals n minus 1 digits, and we have this expression. 1 minus 2 times PL. PL in our case is P of XL equals 1, given YL because of memorylessness. Okay. So just to simplify notation, writing an even number of ones in X, we just say SPC, as we say single parity check constraint. So P of X equals 1 given Y and SPC is 1/2 times 1 plus 1 minus 2 times the channel transition PDF. P of X given Y. This is equal to 1 minus the probability that X is equal to 1 given Y and the single parity check constraint. So now we can rearrange this a little bit because we can take this guy and put it on the other side. So we can say that 1 minus 2 times the probability that X equals 1 given Y and single parity check constraint is the product of 1 minus 2 times probability of XL equals 1 given Y. Now we apply equation 2. You can go back just a moment to see equation 2. Equation 2 is over here. So it says that 1 minus 2 times P of X equals 1 is the hyperbolic tangent of L of X divided by 2. So let's do this. So we apply equation 2 and we get the hyperbolic tangent of L of X1 given Y single parity check constraint divided by 2 is the product of the hyperbolic tangent of L of XL given YL divided by 2. So L of X1 given Y and the single parity check constraint is, we want to extract the log likelihood ratio. So we need to apply 2 times inverse hyperbolic tangent of this product. Okay, so this is essentially the map decoder for bit x1. So we have the log likelihood ratio, the a posteriori log likelihood ratio of bit x1. And we can make the decision x1 hat is equal to 0 if this expression is larger or equal than 0. And we make the other expression equivalently if this expression is smaller or equal than 0. So we have the map decoder for the single parity check code using this expression that seems a little bit nasty first, but we're going to see how we can easily simplify this expression very soon. So how does that relate to LDPC codes? Well, in LDPC code, the the check nodes of an LDPC code, they are essentially single parity check codes. So they are single parity check codes of length D, where the bits are transmitted over the graph. They are not transmitted directly over the channel, but they get information from the graph. So here we get our information from the graph. This is L of C1 up to L of C4. And again, we use the same approach as before. So once the message passing decoder has gathered DC-1 messages, it can calculate an outgoing message. And this outgoing message is 2 times the inverse hyperbolic tangent times the product of the incoming messages divided by 2 and hyperbolic tangent of those. Again, we exclude this message that we calculate from the computation. Very similar to the soldier counting problem, we don't tell the soldier in front of us what he already knows. We tell him everything else that we have accumulated and tell him this. Okay, we are now ready to formulate the sum product decoding algorithm in LDPC code. We now have all the bits and pieces available, and now essentially in the next video we can formalize the sum product decoder.